Hello class, Mr. Cordova here, bringing you section 8-2, areas of trapezoids, rhombuses, and kites. Let's get our lesson objectives for this lesson right now, which are to use formulas to find the area of a trapezoid, to understand the properties of a trapezoid, to use formulas to find the area of a rhombus or a kite, and to understand the properties of a rhombus and a kite. So let's get rolling with our first key concept, which is the height. The height of a trapezoid here is the perpendicular distance h between the bases. So if we take a look here at our trapezoid on the right, we know that we have a trapezoid because the opposite legs here, these legs are not parallel, and we have these opposite sides are parallel, which is what makes it a trapezoid. So we have base and a base, two bases, and our height is measured distance from base to base, from this vertex right here, and we draw a line that is perpendicular to the other base, as we can see here marked with the 90-degree symbol. This is our height. It is very similar, as a matter of fact it's identical to the method that we do to find the altitude of a triangle. Alright, so we're going to take a look at some examples, but before that we're going to take a look at our Theorem 8-4, which states the area of a trapezoid, and the area of a trapezoid is half the product of the height and the sum of the bases. So here we have this trapezoid, we have base 1, base 2, and the height. So we would say the area, and I usually, because I'm dealing with a trapezoid, I call it ATR. You don't have to call it that, but I do it so I know I'm dealing with the area of a trapezoid. The area of a trapezoid is going to be 1/2 the height times the sum of the bases, B1 plus B2. Let me make that a better B there. And that's the area of our trapezoid. Alright, so that's what Theorem 8-4 states. Now let's take a look at a couple of examples where we can use this and move along. Okay, so in here, example 1 part A. Example 1 part A says approximate the area of Arkansas by finding the area of the trapezoid shown. Now they have the state of Arkansas right here in this drawing. It is surrounded by a trapezoid here in red. We have two bases. One base is 250 miles, the other one is 190 miles. They do give us the height, which happens to be 212 miles. So we can actually go ahead and use our newfound formula to find the area of the state. So we're going to be using the area of a trapezoid. So the area of a trapezoid is area of a trapezoid, and that TR looks terrible, so let's see if we can make a better one. ATR, that looks as good as it's going to get. So that is going to be 1/2 the height and the sum of the bases, B1 plus B2. Alright, so we need to find out what our bases are and whether we use B1 or B2 to label these. As long as we know that the 250 and the 190 are our bases, it doesn't matter how we label them. But for me, I'm going to say that this is my B1 and the 190 is going to be my B2 and this is going to be my H. Well, it's the only thing that it can be. So we just plug those numbers in and we have 1/2 times my height, which is 212. Actually, it's 242. It's 242. Looking at sideways from my angle right now. 242 plus 250 times 250 plus 190. There. All right, so then we go ahead and clean this up a little bit. Going through the parentheses, I can clear that up and I get that that is 440. And 1/2 of 242, I can go ahead and say that that's 121. Then 121 times 440, it comes out to be 53,240. And our units are in miles, right? Miles here, miles there, miles here. So this is going to be also in miles, but we're dealing with area, so it's going to be miles squared or squared miles. So the area of the state of Arkansas based on the measurements in this diagram is 53,240 squared miles. Okay, now let's take a look at an example that is yours to do. Alright, as usual, as soon as I finish reading it, pause the video, give it a shot, and then see if you get the same answer as I do. And it goes, find the area of a trapezoid with height 7 centimeters and bases 12 centimeters and 15 centimeters. Good luck. Alright, so now we have just the measurements right here. So we know that the area of a trapezoid, is defined as 1/2 the height times the sum of the bases. So we know that the height is 7 centimeters, so we can say that this is h. The bases, like I said, it doesn't matter what they are as long as we know their bases. So I'm going to call this one base 1, this one base 2, and then we're going to plug those numbers into our formula here and let it go. So it goes 1/2 times our height, which is 7, right, times 12, and I close the parentheses prematurely, 12 plus 15. Now that we have that, we can say that 1/2 of 7 is 3.5, and 12 plus 15 is 27. So 3.5 times 27 gives me 94.5, and our units are in centimeters, so it's going to be centimeters, but area is square units, so it's squared centimeters. So our answer is 94.5 squared centimeters for the area of that trapezoid. Alright, moving on to our next example. Alright, now it says finding area using a right triangle. Find the area of trapezoid PQRS. Leave your answer in simplest radical form. In simplest radical form. So we take a look at the rhombus here on the right, and we are told that SR is 5 meters. We know that PQ is 7 meters. We know that this angle here is a 90-degree angle, and we know that this angle here is 60 degrees. So we're trying to determine our height. We don't have a height. We don't know how far that is. We don't know the altitude. So what we're going to do is draw it out. So we're gonna have to make a segment from S, point S right here, to our base, from one base to the other. So we go from this vertex S to down here to PQ. So it makes a 90-degree angle. So we're gonna get and do that. And let's see, like something like so. And this is going to be 90-degree angle right there, which now, if you notice here on the left, we now have a right triangle. Now, if we have a right triangle there, if this is 90 degrees here, that means that now I have a parallelogram right here, right? So that means that this little piece right here, I need to know what it is. So it's the difference between the two bases, right? So it is 7 minus 5. So this measurement over here is going to be 2 meters, right? So I need to find this measurement h. And there are ways to actually do this if you are familiar with standard triangles, right triangles. So, but I'm going to approach it by using some basic trigonometry. So let's take a look. We know this angle right here is 60. So in reference to this angle right here, angle P, which is 60, we have h and we have this 2 and we have this hypotenuse over here, but we have these two values right here. So in reference to this angle, we have the opposite, which is our h, and we have our adjacent, which is the 2 meters. And there is one trig function that actually represents those two, or it makes use of those two measurements, and the one that we're looking for is tangent. Tangent is opposite over adjacent, right? So to find h, this is what we do. We know that it is tangent of 60 equals my opposite, and the opposite is h, divided by the adjacent, which is 2 meters. Then I solve for h, so I take this 2 meters and I multiply everything by this 2. I'm just going to remove the meters for the calculation's sake. So I multiply everything by 2 and I get that h equals 2 times tangent 60. Alright? So once we do this, we calculate tangent 60. Tangent 60 happens to be the square root of 3. The square root of 3. So we go and substitute that in. We say 2 times the square root of 3 is 2 times the square root of 3. And that is our h. H is 2 times the square root of 3. 2 times the square root of 3. Alright? Now we have the height. We know the measurement of our bases. We can go ahead and use our area of a trapezoid. And the area of a trapezoid, again, is 1/2 the height times the sum of the bases. Base 1 plus base 2. Plug those numbers in, and we have 1/2 times 2 times the square root of 3 times our bases, which are 5 plus 7. Now if we come over here, you notice we have 1/2 and a 2 over here. That means that the 1/2 and the 2 disappear, just leaving me with the square root of 3. So the square root of 3 and 5 plus 7 is 12. So when I multiply 12 times the square root of 3, 12 times the square root of 3, I get 12 times the square root of 3. And our area is supposed to be in meters, but is area, so it's squared meters. And we already are in simplest radical form because 3 is a prime number that doesn't have any other, well, because it's a prime number, it doesn't have any other factors besides itself and 1. So we can leave it as that. This is our answer right here. Okay? So in this particular case, we had to use some trigonometry to find the height. And once we found our height, just plug in those values and work from there. Alright? part B is yours to do. So I'm gonna move this example right over here so everything is on screen. So in example 2, suppose h is made smaller so that the measurement of angle P equals 45 degrees, while bases and angles R and Q are unchanged. Find the area of trapezoid PQRS. Have at it. See if you can get it. All right. So in this particular case, we need to actually find what that new h is. So we still need to do the same concept that we did on the previous problem, part A. So I'm going to go ahead and draw the piece of rectangle that we need. So I'm going to put a piece of triangle, rather, the piece of triangle that we need. So we have a triangle right here, like so. We know that this is 90 degrees here, and this is now 45 degrees. This is still 2 meters, and we need to find h. So the fact that we're using tangent does not change. So we're going to say that tangent of 45 equals height, which is our opposite, over adjacent, which is 2. And we solve for h, and we get that h equals 2 times tangent 45. All right. And it just so happens that tangent of 45 degrees is 1, so is 2 times 1, which is 2. So our height is 2 meters. So we go ahead and we use the area formula for a trapezoid. Area of a trapezoid, again, is 1/2 the height times the sum of the bases, base 1 plus base 2. And we go 1/2 times 2 times the sum of the bases. I'm just going to go ahead and plug in that length, which is, we know by now that is 12. So we say, notice that this 1/2 and this 2 disappear, right? 2 times 1/2 is just 1. So our answer here is going to be 12. So that's the area, and it's going to be 12 meters squared. And that's the area of our trapezoid. Okay? Moving on to the next thing is Theorem 8-5, which deals with the area of a rhombus or a kite. The formula here, the concept here applies to both a rhombus or a kite. So it says the area of a rhombus or a kite is half the product of the lengths of its diagonals. One thing to note, a rhombus is a parallelogram, and one of the properties of a rhombus is that the intersection of its diagonals is 90 degrees. Each of these interior angles right here at the intersection is 90 degrees. We're going to be using that fact in a little bit. So what this actually says is that the area of a rhombus, so area, and I call this one area RH, equals 1/2 times the product of the diagonals. So we have D1 times D2. And that's the area that we can use. We can actually use this for either a rhombus or a kite. All right. Now let's take a look at our first example using this formula to put it into practice. And here we have. Now, notice here that we don't have all the lengths that we would like given to us, but we can actually do this no problem. So here goes like this. The area of in this case we're dealing with a kite, so it's the same thing. So area, And since I'm dealing with a kite, I denote it with area KT. Area of a kite, we know is going to be 1/2 times diagonal 1 times diagonal 2. Alright, again, just like we did with trapezoids, in this particular case, it doesn't matter which diagonal is which as long as you multiply the two. So I'm going to say that my D1 is going to be the sum of the 2 meters here and the 5 meters over here. So we know that D1 is going to be 2 plus 5, and D2 is going to be 3 plus 3. Let me draw a better 3 than this. Oh, that looks even terrible. There we go. So we have a 7 here and a 6 over there. So we plug those numbers in and we get 1/2. The first diagonal is 7. The second diagonal is 6. And we have 1/2 of 42. And 1/2 of 42 is 21. And since we're dealing with area, the units here are meters, right? So it's meters. And the units are squared because we're dealing with area. So it is 21 squared meters. That's the area of that kite right there. All right. Moving on to part B, which is yours right here. So it says, find the area of a kite with diagonals that are 12 inches and 9 inches long. Have at it. All right. In this particular case, and I do say that particular word a lot, but it's like this. We still use the area of a kite or a rhombus, right? So area of a kite is 1/2 one diagonal times the second diagonal. So we know that one diagonal, as a matter of fact, I'm just going to label them here, D1 and D2, like so. And then we're going to say 1/2 times 12 times 9, right? So this is going to be 1/2 times 108, and 1/2, 108 is 54. 54. Our units are in inches, and we're dealing with area, so our units are squared, so it's going to be squared inches. So that's the area of this particular kite that we were told. All right. Moving on to rhombuses. Example 4. Example 4 says find the area of rhombus ABCD. Right here on the right, ABCD, and well, we can actually use the area of a rhombus, and the area of a rhombus, area of RH, is 1/2 the product of the diagonals. Let me actually make that 1/2 look better. There you go, 1/2 D1 times D2. All right. Now here is one issue that I have, or that we have in this problem. I have this length EC right here is 12 meters, and BC over here is 15, but I don't have anything else that I can do to find the length of BD. I need to know BD so I can actually do this. But then we go back to the fact that we're dealing with a rhombus, and we know that the interior or the intersection here of the two diagonals, these diagonals are perpendicular to each other, so each of these angles is 90 degrees. Now taking a look at this triangle that is created is a right triangle. So one thing that I can find out is that I know that I can calculate this length with the Pythagorean theorem. So this length BE, I need to find it. One thing also to note is that the diagonals of a rhombus also bisect each other, meaning that they split each other, and the intersection, they split each other in two. So if EC is 12, AE is also 12 meters. So whatever BE is, ED will also be the same length. But back to the fact that we need to calculate this. So the Pythagorean theorem, and the Pythagorean theorem, if you remember, says c squared equals a squared plus b squared, right? Where c is my hypotenuse and a and b are the other sides of my triangle. So here's what we actually do. We know that 15 is my hypotenuse. Why is it hypotenuse? Because it's directly across the 90-degree angle. So we know that 15 is my hypotenuse. So I'm going to go ahead and plug those calculations in. So right here, 15 squared equals BE squared, right? The length here, I'm going to call it BE, right? It's BE. BE squared plus 12 squared. Okay, so we go ahead and square 15. 15 squared is 225 equals BE squared. Let me actually fix that E. BE squared plus 144. Then we subtract 144 from each side, and we get that BE squared is 81. Then we take the square root of both sides, and we have BE equals the square root of 81, which gives me BE to be 9, but it's 9 meters, right? So we know that this is 9 meters, and if BE is 9, so is ED. So this is 9 meters as well. Now we know, or we can at least find the full length of each of those diagonals. So let's go ahead and do that. So that means that D1, and like I said, you can pick whichever diagonals you want to call D1 or D2. I'm going to pick the 12 to be my D1, the pair of 12s. So I have, it's going to be 12 plus 12, or 2 times 12, whichever you prefer. So we have, this is 24. D2 is 9 plus 9, which is 18. Then we go back over here to our area formula, and we have 1/2 times my diagonal of 24 times 18, and we get that this is 1/2. 24 times 18 is 432, and half of 432 is 216, and our units again are in meters. So we go meters over there, but we're dealing with area, and area is squared, so it is square meters. So there is that answer, and that's how you find the area of a rhombus. All right, using that formula. As long as you know the diagonals and you know how to calculate the diagonals, if you're not given them specifically, then this is how you do it. All right, part B. It's actually for you to think about. We're gonna go over it too, but I'm just gonna put it in here so we can read it, and then I'm gonna put the diagram back. All right, in example 4, explain how you can use a Pythagorean triple to conclude that the length of BE equals 9. All right, give that one some thought and see if you arrive to the same conclusion. All right. So we're taking a look at the diagram, and I should have left that on screen, but it's right there. All right, so how else could I have found that BE right here was 9 without having to use the Pythagorean theorem? How can we? All right, so I'm going to do something over here. I'm just going to move it. I'm going to redraw that triangle right here. So we have our triangle like so, and this is going to be our length BE right here, and we know that this is our 12 and this was given to us to be 15. All right, back when we were dealing with right triangles, we went over something known as a Pythagorean triple, which is a set of 3 numbers that apply to the Pythagorean theorem, and they had to be 3 whole numbers that make the Pythagorean theorem true. So if I had a set of 3 numbers that this relationship applies, then that would be a Pythagorean theorem, a Pythagorean triple rather. So I'm going to take a look at these 2 values that I have. I have a 12 and I have a 15. So I need to find out if I can find a Pythagorean triple. So the most common Pythagorean theorem, or one of them, is the 3, 4, 5. 3, 4, 5. So if I have a right triangle in which I have one of its legs here is 3, the other leg here is 4, that means that by the Pythagorean theorem, my hypotenuse is going to be 5. That is one of the most commonly known Pythagorean theorem, Pythagorean triples. So let's actually see if this actually works. So let's take a look. If I take a look at these lengths, I have 12 and a 15. Well, they seem to have something in common. In particular, this 12 looks like is, and the 15, they have what, 3 in common? So if I pull that, I have 3, and this will be a 4 right here. 3 times 4 is 12. Then I have this 15, and this looks like it is 3 times 5. And what do you have? We have 4 here. We have 5 over here. That means that this side over here should be 3. And since our 15 was arrived by multiplying it by 3 times 5, and the 12 arrived by multiplying 3 times 4, that means that if I take this 3 and multiply it times 3, I get my 9. So that's one way in which we can actually use Pythagorean triples to say that BE equals 9, and that was 9, what was it? Units? 9 meters. So this is 9 meters. And that's how we actually use Pythagorean triples. Alright? This concludes this one lesson right here. So if you guys have any questions, feel free to email me as usual. Please do so. Also, if you have any questions, you may contact me through Teams. I'm always available from 7 o'clock in the morning until roughly 10 o'clock at night. So please, if you have questions, feel free to contact me. Good luck, stay safe, and I'll see you on the next one.